All right, geologic time. Oops. So the Earth is billions of years old, and we need a way to sort of tell that story of time. And so what scientists have come up with is what's called the geologic time scale, or the GTS for short. And it's the system of dating that relates geological strata, so those layers of rock, to time itself. The deeper the whatever rock we're looking at is on the Earth, the older it is. The closer it is to the surface, the younger it is. And it's used by geologists, paleontologists, and other Earth scientists to describe that relationship between major events, maybe new creatures found in that fossil record, to Earth's history, that timeline of Earth. So this is like a really, really big specific one. I didn't make it that big because it's kind of like an overload of information. But here's one that's a little bit easier to handle here for us. So I want to break down some of these new terms. You're not going to be like quizzed on what each of these is defined as, but I just want to go over the terms so that we're familiar with them if you ever hear me talking about it. So our largest measurement of time is called an eon. So looking at our GTS here, the eon is the first column here, and there have been 4 eons. We are currently living in the most recent one, obviously, but, whoop, there goes the lights again. The first 3 actually were before that Cambrian explosion. They are what's considered pre-Cambrian. And ever since the Cambrian explosion, that Cambrian period, we've been just hanging out in this one eon. And eons are super duper big units of time. So to better split it up a little bit, we're going to move on into a little bit shorter of a time period called an era or an era, depending on how you like to pronounce it. These eras break up that giant eon. They're still pretty big, large units of time. So we're going to break those up one more time into periods. Periods are where we're going to start hearing terms that are a little more familiar. Triassic, Jurassic, Cretaceous, those are our dinosaur periods. Cambrian, like our Cambrian explosion. Permian, you may have heard, there's a big extinction event called the Permian extinction. So some of these should start to sound a little more familiar. But periods are still really, really big units of time. And that leads us to our now smallest on our GTS period of time called an epoch. And this is a unit of time that we can actually count. We can use specific amounts of time or even years to date things. If you notice on our GTS here, there are only epochs in this current period that we are living in. And that's because we couldn't physically measure or even reasonably measure smaller units like epochs before our current era. And that's because we didn't have a lot of stuff, that there are big, big gaps in our geologic record. Maybe some fossils just didn't quite get there. Maybe they have been ruined in some way because of geologic processes. So our epochs are really focused on our current era of Cenozoic. So just a few terms, just so that you're familiar with them. So we went through this GTS. We're talking about rocks. Who cares? Why does it matter what happened millions and billions of years ago? Well, it helps us understand Earth's history. What happened before humans? What happened before dinosaurs? What happened before the Ice Age? And in my opinion, it can be kind of fun to solve this puzzle. We see these fossils. Some things are appearing, some things are disappearing. What order do they go in? What came before humans were able to document things on, paper, in writing, in cave paintings? Without rocks, we never would have discovered fossils, obviously. We would have never discovered these creatures that aren't around anymore. And it answers questions about why there are extinct species and extinction events. We know dinosaurs existed, they are in the fossil record, but why aren't they here anymore? We know things like woolly mammoths, ground sloths, saber-toothed cats existed in the Ice Age. Why aren't they around anymore? So we lightly touched on mass extinctions on Wednesday, but I do want to go a little bit deeper into the 5 that we know for sure are confirmed. And I kind of want to look at the specific reasons why we think they happened. So with our first mass extinction here, about 440 million years ago, about 85% of species, boom, gone. That's a lot. Mass extinctions need to be at least half of all life gone. So 85% is well over that 50% threshold. And it's suspected that it was caused by continental drift and climate change. We have the ground moving around. Maybe, a continent floated to where this specific species isn't acclimated. It's not evolving to adapt to that new environment. Climate change, maybe it gets too cold or too hot. These species can't adapt fast enough and they die out. The next mass extinction, about 80%. So not quite as big of an event, but still 80% is significant. Suspected cause, low oxygen levels in the oceans. So all of those aerobically respirating creatures that live in the oceans, they're not getting enough oxygen. They're dying out. Air temperatures are getting colder. Volcanic eruptions. So when we have lots and lots of volcanoes, they're erupting, they're spewing a bunch of ash, soot, materials, gross stuff into the atmosphere. And if there's enough of it, it's going to get into the atmosphere and start blocking out the sun. If there's not enough sun, things get chilly. And if I'm not adapted for that colder weather, I'm gonna die. It's also possible that there were sort of meteor strikes. Maybe there was a rain and barrage of space rocks coming and killing a bunch of things, kicking up more dirt into the atmosphere. Again, decreasing that air temperature. Next up is the biggest of all, the Permian extinction. This is one of the most important mass extinctions. 96% of all species go extinct. 96%. That's an enormous number. We're not quite sure what major event could have such a dramatic impact, but it is suspected. Maybe some asteroid strikes, maybe some more of those space rocks coming in, hitting the Earth, barraging all of these poor species who have no idea what's going on. Space rocks, we're dead. More volcanic activity, climate change. Again, that volcanic activity spewing stuff into the atmosphere that will change the climate of the whole Earth. Maybe it was possibly microbes. A new species of microbes came and it started eating everything and killing everything. We're not 100% sure, but these are just some good hypotheses. Next up, Triassic, Jurassic. This one barely hits that mass extinction requirement. About half of all the species are gone. Again, volcanic activity, climate change. Are you seeing a pattern here? Possibly the pH of sea levels is changing. If I'm not adapted to a more acidic or basic pH, I'm gonna die. My least favorite extinction event, the Cretaceous Tertiary, or the KT extinction. This is the one that kills all of our dinosaur friends. About 75% of our species, boom, gone. Suspected cause, perhaps an asteroid or meteor. This one is very, very well sort of accepted because of all of the evidence. It's not 100% confirmed. Obviously, no one was there to observe it or document it, but it's pretty much believed that it was a giant space rock of some sort that we kind of talked about on Wednesday. And lastly, it is highly likely, very, very likely, that we are currently living in another mass extinction event. Species are dying like crazy. There are species we don't even know about that are dying. We haven't discovered some of these species, and who knows? We'll never see them because they're just dying and we don't know about them. Suspected cause, global climate change, human impacts. So there's a trend here, climate change. Most of these are caused by some sort of climate change going on. And climate change there's an argument that climate change is a natural process that happens on Earth. It happens. It's something, it's things are going to change, whether it's caused by volcanoes, maybe it's caused by humans. But for us, yes, we are seeing an increase in global temperatures, but humans are accelerating that. It is a human-driven climate change. So it does happen naturally, but humans are just making it happen a lot faster, which is killing off organisms because they can't adapt quickly enough to these drastic changing temperatures. All right, so we see all of these mass extinctions. How do we even know that they happen? Fossils, of course. We see fossils of creatures that we've never seen before. They obviously existed. We have evidence that they existed, but they're not hanging out anymore. They're not around. We can't observe them as alive creatures. So something must have happened to cause these creatures to no longer exist. And they also give us things that are called index fossils. Index fossils are fossils that are very widely distributed across the world, different continents. And they're only present for a very, very short amount of time. If, let's say, we have a creature that was alive for 50 million years, that's a really, really long time. It's like maybe not in the grand scheme of things of like how old the Earth is, but 50 million years is a significant amount of time. So we don't know, maybe this creature existed, from here to here, this time, and it's not very helpful in figuring out how old other fossils are compared to that because it lived for such a long time. Index fossils, very, very short amount of time, maybe it was like only 1 million years. So it's much easier to pinpoint where it occurs in that fossil record. And based on other fossils, we find how far it is above or below that index fossil can tell us of more relative age of that rock or fossil. So here are some index fossils that we already know about that we're using still to this day. We got some little trilobite guys. They look kind of like horseshoe crabs. We got lots and lots of shells. This one looks a little bit like a nautilus. And we use shells because we have a lot of fossils from the ocean. There was a lot of aquatic life. There still is a lot of aquatic life because oceans are very habitable places. They have water, which is obviously very essential to life. They have abundant food sources, lots of plankton, lots of other sea creatures. We have photosynthesizing algae that, when we look at a food chain, the algae is photosynthetic. Then we have some things that eat the algae, and then those things get eaten by other things, et cetera, et cetera, et cetera. But the best part about oceanic or aquatic fossils is that there's a lot of them. When we look at the process of creating a fossil, when something dies in the ocean, it sinks to the bottom, and then it pretty quickly gets covered by more sediment or sand or whatever, is churning up at the bottom of the ocean. And then it just kind of sits there. So we have a lot of fossils from the ocean. We do have terrestrial or land fossils as well, but it's a lot harder to find them if it wasn't caused by some sort of mass extinction. Because we have creatures that are scavengers, they might take something and move it, and so it's not like sitting in the same place for long enough to fossilize and get embedded in rock. Maybe we have other factors. It's windy, so some skeletons are getting blown around or whatever. It's not as easy to fossilize on land as it is in the sea. So that's why most of these are very shell-like. Okay, now I want to talk about the cosmic calendar. This stuff gets me really excited. So if you've watched The Cosmos with Neil deGrasse Tyson, the more recent one, not the one with Carl Sagan from like the 80s, but the more recent one, I think it was a few years ago, I believe Neil deGrasse Tyson did something really similar. He kind of walks through the history of the universe. I'm someone who subscribes to the Big Bang Theory. I think it is a very reasonable hypothesis of the start and beginning of our universe. So this one kind of hits on the Big Bang Theory here. So if the creation of the universe happened in, an instant, like the Big Bang, that would have happened right at the beginning of our cosmic year. I'm using a calendar because calendars are something we know and can relate to pretty well. So the Big Bang would happen January 1st, 12 o'clock midnight. Boom. All of a sudden, there's all of this stuff, space stuff. February, March, and April, we're starting to consolidate all of that space dust, rocks, things like that. We're forming galaxies, planets, suns, all that fun, good stuff. Around May, so we're already in the 5th month of our cosmic calendar here. Around May, that's when our galaxy is formed, the Milky Way. And then we continue in that Milky Way, creating more and more solar systems, planets, stars, moons, And it's not until September. So we're already in the 9th month. Already in the 9th month. That's when our solar system is being created. We have our sun. It's got this giant gravitational field because it's so massive. It's sort of condensing all of these random space dusts, particles, and rocks into our planets, moons. And finally, in October, so we've from the beginning of our universe until October, millions and billions of years, we're finally on Earth and we're creating oxygen from our photosynthesis. November, we're getting our eukaryotic cells. They're going to the endosymbiosis. And it's not until December, the very last month, that we're getting multicellular life. Things that are more than one cell. All right, now we're going to zoom in a little bit on December, break down the timeline a little bit more. So this is a lot like our GTS here. We have a very wide, and we're starting to break it down into smaller and smaller units of time. So let's zoom in here on the middle of our month of December. Not a lot is happening until about halfway through December. So on the 15th, we're starting to see the first fossils in our fossil record. We're seeing some bones and shells, vertebrates are coming around, plants, fish with jaws, so that can actually like move their mouths open. It's not like a sucker fish or a filter feeder, actually being able to open its mouth. Insects are coming around by the 21st. Amphibians, we have creatures starting to come up out of the oceans, out of the water. Aquatic animals are starting to become more terrestrial. Reptiles. And December 24th, so we're really getting towards the end of December here. Pangea finally forms. We're starting to see things like dinosaurs, mammals. Birds are evolving from dinosaurs. Skipping up to December 29th, getting real close to the end of the year here. We're finally getting what we like to talk about with dinosaurs are more familiar dinosaurs like tyrannosaurs, like T-Rexes. December 30th, second to last day of the month. Boom, the K to extinction. A giant asteroid comes, wipes out all our dinosaurs. The age of mammals begins. On the last day of the last month, finally, apes, monkeys were starting to come out, become a more dominant life form. 8 o'clock in the evening. 8 o'clock in the evening. So we're in the last 4 hours of our last day of our year here. Humans are diverging from apes. 9:25, we're getting upright, more Homo habilis. Human brains. 10:30, we're finally developing brains that are larger than monkeys. We can do more advanced thinking. We're making tools. 11:52, last few minutes here. Modern humans, Homo sapiens. 11:56 to 11:59, we're migrating. We're spreading across the different continents. We're becoming the most dominant life form here. Now we're going to focus in on the very last minute of the very last day of the very last month of our year. So the Big Bang, first instant of our year. Now we're in the last final minute. We're starting to see evidence of our humans. We're looking at cave paintings, ancient Egyptians. Agriculture is starting to come out here in around, go away soon, in our maybe 24-ish minutes, 23 minutes. Finally, agriculture. We're not nomads anymore. We're starting to set up camp. Dynastic China begins in the last 10 minutes. And finally, in the very, very last seconds, the last blink of an eye, we have a human life. Less than a quarter of a second in this grand scheme of things. That's a human life. So if you ever feel insignificant, don't look at this. Make the most of your life. Make an impact. All right. So let's move on a little bit to continental drift theory. We're going to shift towards more geology and less about time. So in the early 1900s, a German scientist, Alfred Wegener, he proposed this continental drift theory. Maybe there's some continents, they're floating around on some molten rock. I'm just going to call it Pangea, this one big continent. And the other scientists are like, "What? You're crazy. What are you talking about?" What we see today is the way Earth has always been. Nothing has changed. Why would it have changed? There's no reason. We're looking at it now. We've looked back through several hundred years. Nothing has changed. The evidence just isn't there, dude. What are you doing? And then he said, hang on. I have some evidence. Look at the way these continents look. They kind of seem like they fit together, like a jigsaw puzzle. When we look at fossil evidence, for some reason, we're seeing similar fossils across oceans. If these continents weren't together, how did these fossils get on multiple different continents that are really, really far apart? Same thing about rocks. I'm seeing the same age rocks on one side that connect pretty similarly if they were fit together, two rocks on a different continent. And lastly, climate evidence. Glaciers. Glaciers are very, very, very old. And we see evidence that glaciers actually held together. They shared a lot of the same continents, one giant glacier. So let's look a little bit closer here. The jigsaw one is pretty self-explanatory. I think I was in about 5th grade when I first started noticing. I was looking at maps and I was like, ooh, that's interesting. Why does South America look like it kind of fit in the crook of Africa there? That's interesting. And so Whitner was doing the same thing, except he was hypothesizing that, yes, actually they did all fit together, not just South America and Africa, but all of these land masses at one point fit together, kind of like a jigsaw. Next up, fossil evidence. So you're going to look at something like this a little very similarly in your activity today. And what he found was, when you look at fossil evidence, we're seeing these bands of the same animals going across different continents. And if these continents were in fact pieced together in one giant Pangea, it would make sense that they're all, living around the same areas. And they're all gonna go in and flow in between the different continents because they were just one big continent. Same thing for rocks. If they were all connected, why wouldn't mountain ranges be together on the same plate boundary where those tectonic plates are, touching? The same age of rocks, the same mountain ranges, things like that. They're finding the same patterns in the rocks, the same age of these rocks across oceans. So at some point, it's very likely that they were together. They were touching. If I take a rock sample that's, I take like a core sample. So we have a really big drill and it drills down and it takes a core from South America. And you do the same thing in Australia. What we will find is that those stripes, that stratigraphy of rocks, all those layers, are going to match up pretty almost exactly. Because at some point, all of these places were connected. They experienced the same time through rock. What happened in this layer happened in the same layer over in India. And what happened in this layer is the same thing that happened in South America and Australia. And this one I think is the most interesting, personally. Glaciers. Believe it or not, glaciers move very, very slowly. I think it's only a few centimeters a year. But they do move. And when glaciers move, what they do is they actually end up carving out pieces of rock. They leave little grooves in rock that they're sitting on. And what we find is when we stick all of these continents together into a supercontinent, where they're all touching and connected right around Antarctica, they all have this evidence of a giant sheet of ice, one big glacier. Super interesting and cool. All right, so we talked a little bit about this supercontinent, plates moving around. So we're gonna cut this really, really short. There's more I wanna talk about because I'm a huge nerd and I like rocks, but I realize we don't have enough time. So we're just gonna do a couple things with plate tectonics here. So if we were to take the Earth, chop it in half, this is what it would look like. It would have a solid core in the very, very center, a liquid core around that, then some mantle or liquid melted rock, and then the lithosphere on top, what we call the crust. So plate tectonics is a theory that explains the structure of Earth's crust and how the reaction of that rigid crust or lithosphere move over time on top of that magma or that liquid rock, that mantle. We are living on the crust or the lithosphere. I'm going to keep saying lithosphere. That should be a vocab word that you hear often. So when, like even the oceans, they're on the lithosphere. There is solid ground underneath the oceans. It's probably a bit thinner than like on the mountains, but there is still crust underneath that ocean water. The lithosphere is in chunks or plates. Each continent is its own chunk. And those plates are floating around. Now, it's not happening like, you know, an ice cube in your water glass. It's happening, but it's really, really slow, almost imperceptibly slow. So what is the evidence we have that this is actually happening? Just look around. Mountains. We have San Gabriel Mountains right outside our doors. Those just didn't pop up out of nowhere. Trenches. If you've ever heard of the Mariana Trench, James Cameron took a submarine down to the bottom of that. It was a huge, big deal. It is super duper deep. It is the lowest point of our lithosphere, of Earth's crust. One of my favorite examples here, near and dear to every Californian's heart, the San Andreas Fault. If you open up Google Earth and you look on California, there is a literal line cutting through California, and that is the San Andreas Fault. Super duper cool. Two plates are rubbing together, and they're creating this line. Volcanoes. The lava that comes out of volcanoes is actually that mantle. It's that liquid, hot rock. So it's actually coming up out of the crust. And one of our favorite examples, I have actually never been to Hawaii, but I have family that lives there, and I'm sure many of you have been to Hawaii as well. Hawaii is evidence of plate tectonics. It is on sort of a plate boundary where two plates are rubbing together, and they are volcanic islands. And what's happening is the Big Island, that's the oldest of our islands. And you can see the sort of chain. It's kind of a sloping line. And what's happening is there are undersea volcanoes, and they're spewing up this magma. It's getting cooled by the water, and it's forming solid rock. And it builds and it builds and it builds and it builds until finally we have an island that breaks the surface of the ocean. And over time, as those plates start to shift, that volcano moves a little bit. And so Kauai over here is a lot younger than the Big Island of Hawaii. And I'm sure in a couple thousand years, maybe even 100 years, we'll have another new island in our Hawaiian island chain, because those plates are moving very slowly, but they are moving. This brings us to mantle convection. So again, mantle is that place right underneath our lithosphere of that liquid molten rock. This is kind of a dramatic GIF, but I thought it got the point across here. So the mantle, again, is this molten liquid rock. It's really, really thick and viscous. It doesn't move very quickly. But this idea of convection is slow creeping motion of Earth's, liquid rock. And the heat currents are creating this movement. So underneath the crust, it's really, really hot. This mantle is fire. If you ever, look at videos of lava, it just burns everything because it's hundreds, thousands of degrees hot. It's super duper hot. And when we think about it, heat rises. And if heat rises, cold sinks. And what convection is this combination of heat rising and cold sinking. Wait for the sirens. All right. I don't know how many of you have like newer refrigerators or older refrigerators, but when I was growing up, we had refrigerators with freezers on the top, refrigerators on the bottom. I think my parents now have a fridge on the top and the freezer on the bottom, but anyway, what was happening was when we made our first fridge freezer combo units, we were taking advantage of this idea that cold sinks. The cold from the freezer is going to sink and keep the refrigerated stuff cool as well. Not as cold as the freezer, but then it's not taking as much energy to cool down that refrigerator because we're using that cold sinking as a way to keep things cooler. And because heat rises, the inside, the core of the Earth is extremely hot. That is the hottest part. and it heats up that magma. It makes it sort of churn because heat rises, so that magma is going to go up. So here we see the magma rising. And then as it hits that lithosphere, that crust, it's going to start moving. Because once it goes up, it's not going to keep going up forever. It's going to hit that crust and it's going to start to push a little bit. And once it reaches it, it's going to cool down because it's not near that really, really hot core. It's near the cooler lithosphere. We know the lithosphere is cooler because we can live on it. We can't live inside the Earth. It's way too hot. And then once it cools down at that lithosphere, it's going to start sinking because cold sinks. And then it'll sink down to the core, which will heat it up. And then we'll get this sort of circular motion going on called convection. Another example of convection, there was a big trend for a while, convection ovens. They took advantage of this sort of action of churning and moving around. It cooked your food faster than a regular conventional oven because in a conventional oven, you just stick your food in the hot box and let it sit there. But this new invention of a convection oven, you put your food in there and there's a little fan that pushes the hot air around, creating this current that makes your food hotter faster, so it cooks your foods in a quicker amount of time. All right, that's it for the slideshow.